Hey everyone, this is Josh with a fun code companion and computer science tutorial for you today. In this video, we're going to be talking about coding our own guitar and bass tuner. And this isn't limited to guitar and bass, you could use it for any instrument that you want. Music is something that I've enjoyed off and on for many years, and I've been really leaning into playing lately. So when I wanted to sit down and work on some code projects, I got the idea to write my own tuner. This is a great project to work on for all levels of coding, and you'll get to enjoy learning some musical and scientific formulas to help you understand sound and implement it in code. So first, let's talk about notes and how we represent them. Most guitars, whether they're a regular guitar, a baritone, or a bass guitar, have a set number of strings and a certain standard tuning. And you can also tune them to lots of different tunings. I'm a big open tuning fan for the music that I like, so I'm constantly changing around what tunings I use for writing and playing. So in general, in Western music, we use something called the 12-tone equal temperament scale, or 12-tet. And we also have a handy way to specify which note on the 12-tet scale and which octave or frequency that note is in using something called scientific pitch notation. And all this really means in a practical sense is we have the note, which is from A to G, including sharps or flats, and then a number to indicate which octave this is in, or which frequency this note will be at. And next, we have something called MIDI numbers. These are used most often for MIDI keyboards, and they're a standard set of numbers from 0 to 127 that represent the exact frequency fundamental note that will be played. And finally, we have something called hertz. This is the actual frequency of the note that is played. And again, most commonly in Western music, we scale this off of 440 hertz being A4 in scientific pitch notation. I'm not going to get super into the details of how these notes and frequencies work, just giving you some background information that we'll use to code this tuner. So let's say, for example, one of my favorite open tunings for a regular scale 6-string guitar is FAC GCE. And this tuning is close to standard tuning, and it is F2, A2, C3, G3, C4, and E4. So how can we take this and convert it to a playable sound using a computer? And then we can use that playable sound to tune our guitar by ear, matching what we hear from the guitar to what we hear from the computer. Well, there's a couple simple steps that we can use to do this, and this is the approach that I took for the HertzHelper application. I'm starting out with a CSV, comma-separated value, customizable list of tunings that I want to appear in my options menu. So I've included several common tunings in the project for standard scale guitars, baritones, and 4 and 5 string basses, because that's what I enjoy. And you can customize this to any set of tunings that you want if you know the notes and can get them to scientific pitch notation. So if you like to play all kind of different open tunings or tunings for metal music, you can customize this to your own needs. And the CSV contains tunings that are listed in scientific pitch notation. What we'll then do is we'll use a formula to convert the SPN notation to the MIDI number, since MIDI numbers represent more so the actual frequencies that we want to use. And then we can convert the MIDI numbers into the actual hertz frequency. So that we'll be using two different formulas for this. Both formulas are really simple, So it makes sense to kind of do this in a stepwise manner. Finally, once we have the actual frequency that we need to be able to hear it for this to be a useful tuner. So we're going to construct a sine wave, which is just a really smooth representation of a particular note, and play that back through the computer. So we'll be using a couple Python libraries for this, and then it'll be easy to tune our guitars based off the sound that we hear. So we start out with our SPN value. So that would be something like F2. And now there's a very handy formula to convert that to a MIDI number. That is, the MIDI number equals 12 times the octave number plus 1 plus the offset. And there's a chart or a dictionary of offsets in the code base that you can view. These offsets are how we go from something like F, A, C, or for example E and G sharp to a particular offset that's used in this formula. And then the octave number is the number that accompanies that note. So for example, the 2 in A2. So once we have that MIDI number then, we can calculate the actual frequency in hertz from the MIDI number. And again, there are actually different ways to do this, which I find very interesting, but we're assuming 440 hertz equals A4 for this formula. That's really common in the United States. So, there's a little two-step breakout for this that I did just to make it a little easier to read the code. We're going to start out calculating our power, or our exponent that we're going to use in this formula. That will be the MIDI number that we previously calculated minus 69 divided by 12. Now once we have that power, we're going to plug it into the second part of this formula to get our final frequency. That will be 440, which is our base value here, times math.pow to our power that we previously calculated. So this is really 440 times 2 to the power that we calculated here. We're using the math library for this as well in Python. That's the standard way to do exponents. So now we have the frequency of our note that we need to play. And we can use two very handy, awesome Python libraries to get this into an actual playable sound. We're going to use NumPy, which is a common computation library, to generate an array of values that will represent our sine wave. So it's actually going to calculate points on a sine wave for our specified duration that we want the note to play. And that's something in the code that's configurable if you want it to play longer or shorter when you press the button. And we're going to use PyAudio to actually play that sine wave. So we don't have to do any low-level audio coding here. We can use a handy Python library for this. And finally, for our GUI, graphic user interface, I'm using tkinter, which is another really common Python library that I've found very easy to use across projects in my code portfolio. So what we end up with then is we have a nice little UI where you can select a configurable tuning from a drop-down menu, and you can change those tunings by changing your CSV file. And then we'll generate a button for each of the notes in our tuning. So for example, F2, A2, and so on. And when you click that button, it will automatically calculate the hertz value that it needs to play, generate a sine wave, and play it through your speakers or headphones. So then you can sit there and tune by ear, which is a great, easy way to do it if you don't have a clip-on tuner or a tuner pedal for an electric guitar or bass. So I found this to be a really interesting project. I always love combining coding projects with my many other interests that I have. It gives me some interest and passion to put into code and learn some new things and how to use computers to have more fun with my interests. So if you're interested in music and you love coding and you love computer science and you want to check this out, As always, the code is available on the Chain Tutorials GitHub, github.com/chaintoots, and it is open source under a BSD license, so you're free to fork it, change it, play with it, do whatever you want with it. As always, I hope you have found this tutorial interesting and informative. Happy playing with whatever instruments you like to enjoy, happy coding, and I'll see you next time.